blast anti-personnel mines. These are the most common type of landmine ever produced, and the one most people picture when the word landmine comes to mind. They were designed to injure or kill a person who steps directly on them, detonating upward with a concentrated explosive force. Their modern development began in the early 20th century, gaining particular momentum during the Second World War, when armies on all sides needed cheap, simple weapons that could slow enemy infantry, protect defensive positions, and deny access to key terrain, without requiring large numbers of soldiers to guard every area. What makes them so significant in military history is their brutal simplicity. A compact casing, a pressure-sensitive trigger, and an explosive charge are all that is needed to turn an ordinary stretch of ground into a hidden hazard. That same simplicity made them easy to produce in enormous quantities, and it is a major reason why they became such a persistent problem long after the wars that introduced them had ended. Countries across Africa, Asia, the Middle East, and Eastern Europe still deal with the legacy of blast anti-personnel mines planted decades ago, and clearing them remains one of the most dangerous and expensive humanitarian challenges in the world today. Bounding mines. These were developed to make a buried explosive significantly more lethal over a wider area than a standard ground-to-level blast could achieve. Instead of detonating at ground level, a bounding mine is engineered to launch itself into the air first, and then explode at around waist or chest height, sending fragments outward through open space, where they are far more dangerous than a low-ground burst. One of the most famous examples came from Germany in the Second World War, a design so feared by Allied troops that it earned the nickname Bouncing Betty. The engineering logic behind it was grimly effective. A ground-level explosion loses much of its energy into the soil, but an airburst disperses its force across a much wider radius, increasing the chances of hitting multiple people at once. Bounding mines became a defining feature of defensive warfare during that conflict, and their psychological effect on infantry was significant. Soldiers knew that a wrong step could send a charge flying up before it exploded, making careful movement through mined ground extremely difficult. They stand out in the history of landmine development, because they represent a deliberate shift from simply stopping movement to dramatically increasing the area of effect. Fragmentation mines. These mines were built around the idea that blast alone was not always the most efficient way to stop personnel across open ground. By engineering the body to throw metal fragments outward at high speed upon detonation, fragmentation mines could reach farther, strike multiple targets, and reduce the effectiveness of cover that might otherwise protect someone from a simple pressure blast. Their development accelerated during the World Wars, as military engineers refined what kinds of materials, shapes, and casing designs produced the most effective spread of fragments. During the Cold War, numerous countries produced their own versions for use in perimeter defense, border security, and infantry support. What makes fragmentation mines particularly interesting from an engineering standpoint is how much thought went into the relationship between the casing material, internal structure, and the resulting pattern of debris. Every detail of the body influenced how fragments traveled. In many conflicts, they were placed along approaches, around forward positions, and near roads, to create zones of danger that infantry could not easily pass through, making terrain itself into a defensive layer that required no ongoing manpower to maintain. Directional fragmentation mines. These represent a more focused evolution of the fragmentation concept. Rather than sending debris in all directions, a directional mine is specifically engineered to project most of its lethal energy forward in a controlled arc toward a likely enemy position or path. The most widely recognized design in this category emerged during the Cold War, particularly in the United States, and became known for its distinctive curved body mounted on folding legs. What set this type apart from earlier designs was the deliberate shaping of force. Instead of burying a charge and waiting for someone to trigger it randomly, a military force could position a directional mine facing a specific corridor, trail, or open area, and cover that zone with precision. In some configurations, these mines were designed to be command detonated rather than victim activated, meaning a soldier with a triggering device could choose the exact moment of detonation. That distinction matters legally and ethically, because command detonated weapons are treated differently under international law than mines that activate automatically. Directional fragmentation mines remain one of the more technically sophisticated categories, sitting at the intersection of traditional landmine design and more deliberate ambush planning. Stake mines. These mines introduced a simple but important variation on the buried mine concept by mounting the explosive body above ground, on a short post or stake, rather than burying it in the earth. That change gave them a different purpose, and made them suitable for environments where burial was impractical. Frozen ground, marshy terrain, dense undergrowth, and rocky surfaces all presented challenges to traditional buried mines, and stake-mounted designs offered a practical alternative. Several countries produced versions of this type during the Cold War, particularly for use in forested or wetland areas, where conventional placement would have been difficult. The elevated position of the mine body allowed it to spread fragments more effectively through open air and vegetation, reaching targets that a ground-level blast might miss. From a tactical standpoint, they were often used to guard perimeters and cover approaches, where natural concealment from surrounding vegetation could help hide them from view. Their existence highlights a broader truth about landmine development, which is that geography and environment have always shaped weapon design just as much as any purely military requirement. Tripwire mines. These are defined not primarily by the construction of the mine body, but by the method used to activate them. A thin wire stretched low across a path, doorway, gap in a fence, or patch of open ground triggers the explosive when a person or vehicle disturbs it. The tripwire concept is one of the oldest and most adaptable in the history of explosive warfare, and it was combined with many different mine body types across different conflicts and eras. Tripwire systems became especially common in jungle and forest warfare, where dense vegetation gave attackers natural concealment along narrow paths and made pressure-activated mines less reliable. Their history runs through the major conflicts of the 20th century, from the World Wars through Vietnam, various Cold War proxy conflicts, and into modern irregular warfare. What makes tripwire mines particularly significant is their psychological dimension. A soldier advancing through potentially mined terrain must watch both the ground underfoot and the air ahead for nearly invisible lines. That constant, exhausting vigilance is itself a form of tactical effect, slowing movement, increasing stress, and consuming attention that might otherwise be directed toward combat. In that sense, the tripwire mine is as much a psychological weapon as a physical one. Anti-tank mines. These were developed to address a completely different military problem than anti-personnel mines. As armored vehicles became central to warfare during the First World War, and expanded dramatically in the Second, armies needed low-cost methods to stop or disable tanks and armored carriers without committing large numbers of soldiers to direct combat with them. Anti-tank mines solved that problem by burying large explosive charges under roads, fields, and likely vehicle routes, designed to detonate under the weight and pressure of a passing vehicle. Their pressure activation thresholds were deliberately set much higher than those of anti-personnel mines, so that individual soldiers walking over them would not set them off, making them specifically targeted at mechanized threats. In the Second World War, both sides used them extensively to channel armored movement, protect flanks, and slow breakthrough attempts. Their influence on the shape of armored warfare was enormous. Tank commanders had to account for the possibility of hidden mines on almost every route, which slowed advances, required specialized engineering support, and made certain terrain far more valuable than it might otherwise have been. Even today, anti-tank mines remain one of the most tactically significant obstacles in conventional military planning. Tilt rod mines. These represent a specialized development within the broader anti-tank mine category. Standard pressure-activated anti-tank mines required a vehicle to pass directly over them and exert downward force on the trigger mechanism. Tilt rod designs addressed a specific weakness in that approach by adding a protruding vertical rod to the mine body. When a vehicle's hull, undercarriage, or lower front plate made contact with the rod, and pushed it aside or tilted it, the mine would detonate even if the vehicle had not yet fully passed over the pressure plate. That made them effective against vehicles that were designed with reinforced undersides, or that traveled at angles across rough terrain, where direct pressure on a buried trigger was not guaranteed. The tilt rod concept emerged in the mid-20th century as a response to improving vehicle armor and changing battlefield conditions. It reflects the ongoing contest between protection and penetration that has defined armored warfare throughout the modern era. Every improvement in vehicle survivability created demand for new triggering concepts, and the tilt rod was one of the more straightforward engineering responses to that challenge. Off-route mines. These differ fundamentally from the mines placed directly in the path of a target. Instead of being buried under a road or trail, an off-route mine is positioned to the side of a vehicle's likely path and aimed to strike from an angle as the vehicle passes. The concept became increasingly important in the later 20th century, as militaries developed better route clearance methods including rollers, plows, and electronic jamming systems that could detect or defeat conventionally buried mines. By placing the threat beside the road rather than under it, off-route designs made those clearance methods far less effective. The engineering behind them often involved shaped charges, or directional explosive elements, that could project lethal force across a distance and penetrate vehicle armor from the side, where protection was sometimes weaker than at the front. In modern conflict zones, off-route mines became especially relevant along convoy routes and supply lines, where predictable vehicle movement made it possible to position a waiting threat at a chosen point well before any vehicle arrived. Their development represents one of the clearest examples of how mine design has evolved in direct response to countermeasures. Scatterable mines. These were created to solve a specific military problem: how to rapidly deploy minefields across large areas without the time, manpower, and exposure that manual placement required. Aircraft, artillery shells, rockets, and specialized ground vehicles were all developed as delivery platforms that could scatter large numbers of mines over wide areas in a very short time. The concept became especially important during the Cold War, when military planners on both sides anticipated fast-moving armored battles across broad fronts in Europe and needed ways to quickly deny terrain, slow enemy advances, and channel movement without committing engineering units to dangerous forward positions. Scatterable mines transformed the scale of mine warfare dramatically. What once required hours of careful manual placement could be achieved in minutes from a safe distance. That capability came with serious complications, however. Rapidly scattered minefields were extremely difficult to map accurately, and in the chaos of fast-moving combat, the locations of delivered mines were often imprecisely recorded. That left significant unexploded hazards across landscapes that were later difficult to clear, contributing to civilian casualties in the aftermath of conflicts where these systems were used extensively. Improvised mines. These are not manufactured military weapons, but homemade or adapted explosive devices used as substitutes for them. They emerged most visibly in the context of insurgencies, guerrilla warfare, and irregular conflict, where armed groups lacked access to industrial weapons production but still needed ways to threaten vehicles, deny roads, and impose costs on better-equipped opponents. Their roots go back well into the 20th century, but they became globally recognized in conflicts of the late 20th and early 21st centuries, particularly in regions where prolonged irregular warfare created strong demand for low-cost, adaptable threats. What makes improvised mines significant beyond their immediate danger is what they reveal about the nature of modern conflict. A manufactured military mine tells you something about state resources, industrial capacity, and formal doctrine. An improvised device tells you about resourcefulness, asymmetry, and the spread of technical knowledge through informal networks. They are also particularly challenging from a clearance perspective, because their enormous variety in design, materials, and construction makes standard detection methods less reliable and prediction more difficult. Training mines. These are inert or otherwise safe replicas of real mine types, produced specifically for instruction rather than use in combat. Every military force that employs mines also requires soldiers, engineers, and clearance teams who understand how to recognize, handle, mark, and neutralize them without triggering them. Training mines make that education possible. Some are near-perfect external replicas of operational models, designed to teach recognition under realistic conditions. Others are cutaway or transparent versions that reveal internal components, allowing instructors to explain triggering mechanisms, construction, and safe handling procedures in detail. Their history is closely tied to the development of mine warfare itself, because as mines became more sophisticated, the training required to handle them safely became correspondingly more demanding. Training mines also play an important role in humanitarian demining programs, where civilian clearance teams learn identification and safe handling techniques before working in real minefields. They represent the educational and procedural infrastructure that surrounds mine warfare. The systems of knowledge and practice that exist alongside the weapons themselves and that are essential to managing both their military use and their long-term humanitarian consequences. Landmines have been part of modern warfare for over a century. They were born out of a simple military need to deny ground, slow movement, and protect positions without requiring large numbers of soldiers to hold every line. Over time, that basic idea evolved into dozens of different designs, each shaped by a specific problem, a specific terrain, a specific target, or a specific gap in what earlier designs could do, from the small buried blast mine to the sophisticated self-deactivating systems of the late 20th century. Every type reflects the ongoing conversation between military need and engineering response.